Okay, hi class. Today we're looking at compound interest. So simple interest is just that, very simple. It's very unrealistic over the long term for long investments and long loans. Today we want to explore interest that reflects much better the way that investment companies or banks or loaning companies would charge interest. And the first thing we need to do is just get some definitions out. So in your package you receive, there's a handout you're going to want to fill in. And there's some key terms that are unique to compound interest. So the first statement here that I'm making is just for you to fill in on your worksheet right here. So you can fill in the blanks as you listen to the audio here. So the statement is this: as investments and loans accumulate interest, a constant rate of growth, in other words, the term interest rate, is applied over time. Now for simple interest, the term interest rate is the annual interest rate and it's applied once. It's applied once, but the amount of time elapsed in years can certainly vary. But that single interest rate, the growth rate, is applied to calculate the total interest accumulated over that time interval. In compound interest, however, it can compound many times a term interest rate, which depends on the compounding frequency. And in your textbook, you'll explore some examples as you read through the section. And you'll also, at the very end on page 432, have a chance to record the most common compounding frequencies, which are annual, semi-annual, quarterly, monthly, biweekly, and daily. And for each of those, there's the number of times that interest is added during the year, and that requires us to adjust the term interest rate based on the annual rate and how many times the interest will be calculated. So in this example, we're going back to the similar initial investment, which was a $1,000 gift that was going to be invested at a 5% annual rate, and here it's compounded annually. So we're going to compare this to the result of simple interest, which accumulated for different amounts of time ranging from 1 to 5 years. As you look at the table, it's structured a little differently here. The first thing you'll observe is that in addition just to time, we need to know the opening balance at the beginning of that term. We need to calculate the term interest, which is what we had done before, and then we're going to calculate the amount at term end. I was calling that the term end value. To start though, we're going to look at calculating the annual interest rate. Well, at 5%, that would be 0.05. When we go from there and we want to calculate the term rate, well, if it's compounded annually, the frequency is once, which means that the term interest rate will be also the annual rate at 0.05 as a decimal. The number of compounding periods, if it's invested for 5 years, will be 5, once per year for those 5 years. Where we get into compounding frequencies that exceed once per year, then the number of compounding periods would be multiplied by the number of years. So for example, semi-annual frequency of compounding would result in 2 compounding periods per year, which would be 10 over the 5-year period. So now let's look at our table and start to fill some values in. Okay, in our first row, our opening balance is the amount invested. That's our principal. The term interest is calculated just using the growth rate, 0.05, applied to the principal, which earns us $50 of interest at the end of that first year. At the end of that first year, we now have our principal plus our interest combined together, which gives us $1,050. Now, the nice thing about compound interest is now the amount that is opening our second year has increased by the amount of the interest. So $1,050 will be the opening balance. Term interest is now applied at a rate of 5% to that 1,050, and then we have a new interest term which we can now add in. At the end of the second year, our balance grows yet again, which opens us up at year 3. Okay, as you can see here, the effect of compounding continues. The 5% constant growth rate continues to be applied to the opening balance, and we can see the effect of the compounding. If we were to compare this to the simple interest values, the amounts earned at each stage were just an additional $50. So the amount of the investment at the end of 2 years would have simply been $1,100. At the end of 3 years, it was $1,150. So the effect of adding on the interest into the opening balance is certainly obvious. And here we'll just pause, complete the rest of the table, the remaining 2 rows, and then I'm going to discuss an alternate way which we can calculate this, which relates back a little bit more to the compound interest formula. Okay, so that completes the final 2 calculations here. For the term end, we would have kept our $1,000 investment and earned $276.29. So the calculation for interest from amount and principal as before, you can include down here in your table. So that's one of the formulas which you need to be able to do. The interest is simply the difference between the final amount and the original principal. Now, if we return to the table that has been completed, in red I put the values for interest earned by simple interest, so $50 at the end of the first year all the way to $250 at the end of the 5th year. Compared to compound interest, we've earned an additional $26 and change. So even at a small interest rate, even with the lowest possible compounding frequency, which is once a year, we have still earned more interest for compounding, and you can see the error would just grow more and more if we were to compare the difference between the amount by simple interest and the amount by compounding. Now, one more thing I want to do with this table is look at the pattern for calculating the term interest. We take 1,000 and we multiply it by 0.05. We take that value and multiply it by 0.05. So the 1,050 that we have in our table is the first value in the sequence here, which is the opening balance, multiplied by 0.05. So now we're at the end of 2 years, we've multiplied by 0.05 twice. The 110250 contains the 1,000 initial principal and 2 multiples of 0.05, and now we're multiplying by 0.05 again. So as you can see, really the more direct way to calculate the interest would be to multiply by a power of 0.05. So that's the first thing that could be mentioned is, for example, calculating the 5788 could be done more directly by taking 1,000, multiplying by 0.05, and it's been compounded 4 times at that point, so we'll use an exponent of 4. So it'd be 4 multiples of 0.05. That would give us the same value. Similarly, when we add back on the opening balance, the effect here is really having multiplied by 1.05, because the initial balance is the full value which we take, plus we add back on the extra 0.05 multiplied by that. So for example, in math we can sometimes do things a little bit more directly, and what I'm talking about here is if you were to multiply, say, 1,000 times 0.05 and get 50, and then you were to take the 1,000 and add 50 to get 1,050, the more direct way to do that would be to multiply by 1.05, which would just give us the 1,050. So the compound interest amount that we actually get can be more directly found by multiplying by 1.05 a given number of times, and the number of times would of course be based on how many compounding periods have elapsed. So at the end of the 5th year, the 1276.29 could be more directly calculated as 1,000 multiplied by 1.05 5 times, so to the exponent 5. And if you calculate that, you'll see that they probably agree very closely. There might have been some rounding there that has taken place, which would result in maybe a slight difference, but calculating it now, it only differs by a penny. Okay, so this of course is the compound interest formula, which we want to summarize in your formula chart here. And this is amount of the investment, starts with a principal, multiplies by 1 plus the term interest rate, and I'll just add a little subscript here, and then raised to the exponent n, which represents the number of compounding periods. So term interest rate can be calculated as well, as shown before. Term interest rate is simply the annual rate divided by the frequency. I'm just going to call it f. Okay. Now let's go back to our chart here, and let's explore this a little bit more. So what we want to do is plot some of these points. We're going to plot the term end, which is the amount of investment according to the number of years. Okay, I'm going to do this on the graphing calculator. I'll have you do this on your graph, and then we're going to discuss some of the relationships that are evident from this. Okay, as we continue here looking at the investigation, I'm following along on page 426, 427 now, and we're pretty much at step 3. So we've looked at the interest earned and seen that there's definite advantage over simple interest when the interest is added and recompounded in the next compounding period. Now in step 3 we're adding a first differences column to our table, which I don't have room for here, but I'm going to use the graphing calculator for. I've looked into the table and I've loaded in the year number, and I've also added the amount at the end of each year for the first 5 years in my second column. I'm now about to look at the first differences between those. So at this point, just to recall, we've done this maybe a couple times in class before. When we're trying to find first differences, we go to a new column, go to the top of the column, and in the header row, we go to second stat, over to operations number 7, and we put in the differences in list 2, second 2. Close bracket, enter. So we can see that the first differences here are really just the interest values. So the interest is not constant from year to year. That's what we expected to see. So obviously it's not linear. We can go to a new column and explore whether or not we think this might be quadratic. Repeat the operation, second list, operation number 7. Now we're going to take the differences in interest values, 2.63 and growing. So clearly this is not quadratic. So there's a nonlinear relationship between the number of years and the amount remaining at each given year. If we were to look at the graph here, zoom 9 would reveal the scatter plot. It looks very linear, and that's because the interest is growing at a very, very small rate. 5% growth is almost imperceptible here. If we were to examine this data and ask for a curve of best fit, many of you would probably draw a line, which would be pretty natural. But the analysis from the table of values reveals it's not linear, not quadratic. And we would see it if we continued exploring our lists, that repeating first differences will also not give a constant value. So this is not a relationship that can be modeled using a polynomial expression. The problem here is we're looking at differences being constant, and what we should be looking for is a ratio. So in step 4 of the investigation, we were looking at common ratios. Now that's of course familiar to us at this point. We've studied geometric sequences where a common ratio was very important. So if we were to go back to our list here and clear out the values in list 3 and list 4 and repeat this for ratios, it'd be a little bit tedious to do with the graphing calculator because there's no quick way of taking the ratio of successive terms, but we could enter it in as we see it, 1102.50 divided by 1050. And look what we get, 1.05. Let's try 1157.60 and divide by 1102.50. Oh, let's try that again. 1157.60 divided by 1102.5. 1.05. 1215.50 divided by 1157.60, also 1.05. And the last one, just to convince you, is shown. So 1.05 is the multiplier. Well, where did that number come from? Well, of course, that's how we calculated the amounts. And I showed that in the calculation for the amount at term end 5, that rather than taking the opening balance at the beginning of the 5th year and multiplying by 5%, we could take all of those 5% multiples, count them up, there were 5 of them. We could also include 1 in the multiplier because we want to add back in the 1,000, and that of course would give us our 1276.29. So we can see that 1.05 has been repeatedly multiplied from 1050 to 1102.50, from that to 1157.63. Another 1.05 as a multiple gets us here, and a final arrives us at here. This, of course, is the compound interest formula. 1 plus term interest rate to the exponent n. So the relationship here is actually exponential. When the formula that governs it uses an exponent which is a variable, this is not polynomial, this is exponential. So the common ratio is in fact the growth rate of 1 plus the term interest rate. We can now at this point start to fill in some information that's relevant to compound interest. The relation type certainly is non-linear and exponential. We can see that no finite differences were constant. And more importantly, common ratio was found. Graphical properties, well, we can see that the common ratio, without the graph here, we would have to go back to the graphing calculator. Looking at the graph, 1.05 doesn't stand out on there as a value unless we go to the equation. The equation of this is really the function equation. We could put it in here as amount of the investment at the end of n years equals initial value 1,000 multiplied by our growth rate 1.05 to the exponent n. And if we were to plot that as a y equals ab to the x, because this is the pattern for an exponential function where we have initial value a, some growth rate b, and our variable as the exponent. This is an exponential function. We could go back to the graphing calculator and insert 1,000 multiplied by bracket 1.05 close bracket to the power of x, and plotting that, we would see it goes through all of our points. So in fact, the graphical properties here would be simply this, that the initial value of the graph equals our principal, which is 1,000, and the growth rate equals 1 plus I, which is in this case is 1.05. Sequence type, well, the values here in our table of values are growing by a common ratio, so this can't be arithmetic, it must be geometric. So our sequence type here is geometric. Oh, I'm in the wrong field here, geometric. And finally, the general term, which we know we've modeled after nth term equals AR to the exponent n subtract 1. In this case would be, I've really already entered it in, but would be T sub n equals 1,000, common ratio of 1.05. Now, let's examine this here. The first term is not 1,000, so let's modify this. The first term in our table of values was 1,050. So, although the function equation used a y-intercept of 1,000, passed through 1,000 on the x-axis. I could see that if I went to the table. Second table set, I'll start at 0. Examine my table there, and the first value when the exponent is 0 for 0 years would just give our principal at $1,000. So that would be from our graph back up 1, the y-intercept. For a geometric sequence, the general term requires that the a value here be the first term. And so I'll just point out that the general form of an exponential function, y equals a b to the x, has been perhaps introduced in the past. The a there is the y-intercept. Here, the a is the first term, term 1. So 1,050, 1.05 to the power of n. So at this point, we've looked at the shape of the graph. We've seen some of the properties. We've seen the sequence type and the connection to geometric sequences. And this is the main connection we want to make that distinguishes from simple interest, is that they are of geometric type in their sequence. The graph is exponential, and it follows exponential growth. The reason for that, of course, is our growth rate is our base for the compound interest formula, 1 plus I. And at this point, you can fill in the rest of this graphic organizer using, as I mentioned before, the compounding frequencies found on page 432. I've given you 2 little bubble spaces to fill that in. And we'll go through maybe some examples in class. Read the section, go through the examples for determining interest rate, varying the compounding period, and calculating compound interest from this section. And I've given you the Blackline Master 7.3 for you to use to practice additional questions.